All right, so welcome back to our Cyber Physical Systems course. And last time, this was the last slide we showed, showing a UML activity diagram for the process of an airplane landing and then basically deboarding passengers and picking up new passengers and taking off again. But I just wanted to continue and talk about other tools. I have in the next slide another example that is still UML based, but they don't have to follow the same type of same features of the diagram. Depending on the tool that you use, the diagram may differ in the way it looks, but the spirit and the engine can still be UML based. The next diagram that I'm going to show in the next slide is done with Simulink sim events. So that is an event-driven type of simulator that is in MATLAB. We don't have a license for that, but we have licenses for two other tools in MATLAB. I know that at TCNJ we love MATLAB, so we do have licenses for two other tools that are very useful. One is Stateflow, and actually I like that one better within MATLAB than any other one. So Stateflow, inside MATLAB, we have that available here, and you can use that to simulate in the same context that we were talking about of a system and a state variable description and definition. Well, you can simulate that in Stateflow, okay? So that's a toolbox that we have in Simulink. The other one is Simscape. That's also another toolbox of MATLAB, and that's where you want to simulate multi-domain type of activities or complex systems. So that one you can mix electronics, electrical, information technology, computer with hydraulic, mechanical, health-related. So basically any type of multi-domain system like that. So we also have that, the Simscape toolbox. So that's three more, Stateflow, Sim Events, and Simscape in MATLAB. We just don't have the Sim Event. And this is how a diagram will look in Sim Event. It's kind of hard to read, but just to give you an idea what the system model would look for a similar type of process. This is also for a similar type of process at an airport of a plane coming in and picking up passengers and leaving. It looks different, but it's modeling the same type of activity. So, as we have discussed, we can have multi-domain systems, and they can include all those that I mentioned: electrical, hydraulic, mechanical. Any type of system can be modeled as a multi-domain system. And the nice thing is that if we use a tool like the ones that I mentioned, you can capture a model of the system at the system level, at the cyber physical system level. And the reason is because in reality, all those systems have primitives that can be modeled with things that you already know, that they embody the mathematical foundation of representations like the Laplace transform. And so all the things that we have discussed, input-output relationship, state variable representation, whether you are considering the system as a continuous time system or as a discrete time system, all those applies at the system level for multi-domain system analysis. And at a detail level, even Laplace transform, C-transform representations, if you recall, you can represent systems, simple systems that you are familiar with block diagrams where the blocks were simple integrators, summers, scalars. In the case of discrete systems, we had cycle delays and also summers and scalars, which are multipliers. So the concept of having a block diagram that really communicates what the system does and it really lets you model the behavior of systems and go back and forth between mathematical representation and a block diagram it's been used for a long time. It's just that the question is, how do we kind of carry those ideas, not necessarily the equations, but those mathematical foundational ideas into complex systems as well. So if we have, for example, a differential equation that describes the dynamic performance of a system, which it could be a spring and you apply a torque to it, so you are transferring that torsion to the spring. So you can have an equation like the one here, and if you look at that equation, because you have conservation of energy and mass, so if you apply the torque T sub A at the end of the spring, it is transmitted through the spring, okay? And that variable in that system, and that's another concept that we want to take to our complex system representations, the concept of through variables and across variables. So that that torque that is being transferred through the spring, that is what we would call a through variable. Similarly, the angular rate that results in the spring as a result of that torque being applied at one end of it is, we can think of it as an across variable. So we in EE or computer engineering, we're very familiar with, we have our own through variables and across variables. Namely, we have current, that's clearly a through variable, and we have voltage, that's clearly an across variable, and that's even how we measure it. So in every type of domain, you have very similar things. And I know that this chart is a little bit difficult to read, but it's not intended to actually sort of get the details of it, but it's just meant to show that whether you have electrical, hydraulical, pneumatical, thermal, translational or rotational systems, you have these types of transversal variable, transit variable, and you can have the product of it, you have relationships between them. You can take the integral of it, and you can calculate things like energy, and you also have even symbols for it, where you can, if you have a thermal system, you actually can have a schematic. And actually, when calculating heat flow and things of that nature, a lot of the same type of analysis and circuit representation are used that we use in electrical circuits. Actually, there are transformations between thermal resistance and electrical resistance, and heat flow and current, and thermal gradients and voltages, such that people that don't have thermal analysis tools, what they use is they use these equations to translate the thermal quantities to electrical parameters. And if they want to simulate a thermal system, they use SPICE, something like LT SPICE, because it's free. So that way they don't have to buy the expensive thermal analysis simulators. So that's done to this day, mainly in the electrical, the electronics engineering community, where they're not using this type of analysis every day, but if they do want to do some analysis of high power type of transistors or heat dissipation on different chips that are running at very high frequencies, that's what we can do. We actually, there are equations to translate from thermal to electrical, do the analysis, get the results. A current is sort of like a heat flow. A voltage is sort of like a thermal gradient, and then you convert back, and you have done, in a roundabout way, your thermal analysis. So it's a trick of the trade, if you will. So the point is that every domain is characterized by the same relationships, okay? And because of this, we can have this multi-domain type of models and simulations that are embodied, you don't have to remember any of this, which are embodied in tools like MATLAB for the system. Also, and I'm glad that they're doing this because they're looking ahead to the importance of complex system. There is was released recently a brand new tool in MATLAB which really tries to look at the system, complex system problem holistically. It's called Model Composer. And it's new in their suite, and of course we don't have it yet, but it's something that is coming, and I think it's going to, for people that are used to use MATLAB, and it's kind of like the tool of analysis and engineering that they use the most, is going to be very convenient that they have that tool as part of the MATLAB ecosystem, and we don't have to go off and look at other tools like Core or things like that, okay? So that, I saw that recently, and I'm very glad that they have invested in bringing that to market. So just to remind you about the principles of linearity. So we have to have superposition if a system is said to be linear, and what that simply means is that if I apply an input x1 to a system and I get an output y1, and then I apply another input x2 and I get an output y2, and then apply a third input which is simply the sum of x1 and x2. That's a third input, is the combination, the sum combination of those two inputs. Then I better get an output that is the sum of the previous y1 and y2 that I got. So if I do that, if I get that, then this principle of superposition applies, which is one of the criteria necessary to claim linearity, okay? Also, if I apply the other criteria to claim linearity is to have a system that is homogeneous. And what that means is that if I apply an input x1, I get an output y1. And then if I apply a second input that is some constant times that input x1, I better get the previous output that I got y1 times the same constant. It has to be scaled accordingly. So that means that the system is homogeneous as well. If I have the principle of superposition hold and the system is homogeneous, then the system is linear. So for example, and you can basically go through the analysis that I just articulated, but do it in paper and basically prove or disprove that a system is, whether a system is linear. For example, if you have a system that is characterized by the equation output y is equal to x squared, then clearly the system is not linear, okay? Because if I put x1, I get x1 squared. If I put x2, I get y2 squared. But if I put x1 plus x2, I don't get y2 plus y1 plus y2, which is x1 squared plus y2 squared. I get x2 squared, x1 squared plus 2 times x1 times x2 plus y2 squared. Okay. So we get that trinomial, right? And the second case, the system also is not linear because I have that b constant always added there. So that's an important actually thing to remember. B is an offset. Offsets are horribly, or make systems horribly nonlinear because of that. If I put, just to use the homogeneous case, if I put an input x1, my output y1 becomes m times x1 plus b. And if I put x2, then I get an output y2 m times x2 plus b. And if I scale that x2 value, then my y2 is m times a times x1. But then I always have that plus b there. That doesn't scale. So b is an offset. So offsets make systems behave very badly in a nonlinear fashion. And we see offsets in all kinds of circuits. So if that offset, and you can get rid of offset if it's in the numerator, okay? So remember that. You can get rid of offsets if they are in the numerator of whatever expression you have. If they are in the denominator, then they're not only an offset that makes the system nonlinear, but they are very difficult to null out, okay? So like if you are basically measuring something like a conductivity, which when you apply the equation, if you have an offset in the voltage, since the conductivity is current over voltage, that voltage offset that we work so much with, I mean, everything is some type of voltage signal, that voltage offset in the denominator, it really makes your system nonlinear and very difficult to nullify, and introduces a lot of error in your system. Okay? So to summarize, a linear system obeys the characteristic of superposition and is homogeneous. Okay? So if systems are linear, then we can use linear transform techniques that you are familiar with. Things like the Z-transform for discrete systems, Laplace transform for continuous time systems. And then if we are going to analyze a system, we can take our system formulation and apply a transform and go to the transform domain, whether it is Laplace or the Z-transform, do our analysis in that domain, get a result, and then apply the inverse transform and get back to our original time domain, let's say. Okay? Why is that useful? Well, because some operations are much more difficult to carry out in one domain than another. So for example, you recall that if I want to know what the response of a system is in the time domain, I have to do convolution. Nobody likes convolution. So if I go to the transform domain, then it becomes a multiplication. Very nice. Easy to do. Okay? So then I can do that. If I wanted to apply a filter, find the response to a filter, I can take the transform of the filter, take the transform of the input, go to the transform domain, multiply that, get my output, that's going to be the transform of the output, invert that to the original domain, and then I have my response in the time domain. Okay? So manipulating systems in different domains or transform domains are important. Filtering is very easy to do in the frequency domain for discrete time systems. For example, you can get very accurate filters. For example, a digital filter with a very sharp response, meaning that you are isolating a very narrow range of the spectrum with a very sharp response, so that outside that band, you're going quickly down by hundreds of dBs. That would take hundreds of cycles or taps if you were going to analyze and implement that in the time domain. But if you were going to do it in the frequency domain, you take an FFT, get the spectrum, plug the band out of the spectrum that you want, zero everything else out except the band that you want, and then take the inverse FFT, and then you have your response. A lot easier. Okay? A lot easier. And that's the result of this diagram. Basically, you went to the frequency domain, did your manipulation, which in this case is just taking that band and zeroing everything else out as a filtering operation, and then go back to the time domain. Okay? So that could be very, you could come up with a very nice filter to reject a specific frequency, for example, which is the opposite. Instead of making everything else zero and keeping a band, you make a band zero and keep everything else. So that a rejection type filter, let's say for rejecting 60 hertz, which is in the environment for medical applications. So for medical applications, the 60 hertz is really invasive to the measurement that you're trying to take. So coming up with efficient and good 60 hertz rejection filters is something that is in all the good type of medical equipment. So that's an example. So again, this is just the reminder of the operations of the Laplace transform. I don't think that we'll be doing any of that for our systems. They're going to be too complex for that, but just as a reminder. But do remember something, that the S operator is sort of a differential operator. Because that idea is going to become in handy. Okay? Just like in the discrete time domain, the z minus to the minus 1, the z to the minus 1 operator is a delay of one clock cycle in this sample clock cycle domain operator. So all the systems, because of what we have discussed, all the system can still be expressed as a transfer function, which is the ratio of a transfer function in the transfer or the transform domain, which is the ratio of the transform domain of the output over the transform domain of the input. So that's always easy to remember. The transfer function of a system is sort of like a gain, okay? And the gain is the output divided by the input. That's a way to remember it. And every system is going to have some type of transfer function that relates the output back to the input. In that sense, we want to carry with us, as we go forward to design complex systems, some concepts that are derived from the simple transfer function body of knowledge. These are stability, So I talked about that last time in the bounded input, bounded output sense. So if you have a system where you input a signal or a stimuli that is bounded, meaning that it is bounded between some values or some space, and it doesn't go off to infinity, you better get at least an output that is also bounded. Now, if it's bounded, but it's bouncing around a range, that system may not be, depending on what the system is meant to do, that system may not be stable, but it's not unstable either. It's what we call marginally stable. And some systems, we do want them to be marginally stable. It's useful that they are that way. So oscillators are such kind of system. But most systems, we want them to reach a steady state, because we're trying to control something. And what we're trying to do is tell the system, this is what we want the output to be. And we want that system to react to our command and control or affect something in the natural world, in that physical world, in some type of a stable, constant fashion. But what are we trying to defend ourselves from? We're trying to defend ourselves from external disturbances that are out of our control. So we're trying to make the system be able to react to those disturbances that we cannot predict, but be able to adapt to them and still deliver the output that we want according to our input or command. So that type of control system paradigm also we're going to carry with us as we go forward. So if we have determined that the system is stable, then we want to be able to do a steady state error analysis. So steady state errors are important, and we still need to do a steady state error analysis, which is once the system reaches a point where that output is not going to change anymore according to the disturbance and according to the input, how far is it from the ideal value that we wanted the system to reach? It could be zero, it could be it could be a finite quantity, or maybe it just doesn't get there. That depends on the order and the complexity of the system. So that's the type of steady state error analysis that we're talking about, okay? So there are system types using the control body of knowledge. And the system type essentially is the number of poles of the open loop transfer function. So if you look at the open loop transfer function without the system having any feedback, just the feed forward part, and you look at the number of poles of the Laplace transform, that's the order of the system, that's the system type, okay? And we also use three types of test inputs to quantify the steady state error nature of a system according to its type or order. We use the step, we use ramp, and we use parabolic inputs. So depending on the system type, the system is going to react differently to the different type of test signals and give you different results in the steady state error sense. So again, you have three possibilities in this respect. You have 0, a finite number, or infinity. And there is a way, once you know the system type, and you know the number of poles, because you know the system type of the system, you can basically calculate whether you're going to get a 0 error, a finite error, or infinity. So again, this is where you can actually have a transfer function for the system, okay? But we're not going to have nice transfer functions for our systems. We're not. But what I want you to remember is that still you have to do a steady state error analysis. You have to define what that is, and you have to define what your test input characteristics need to be to try to find what the conditions at which you get perhaps 0 steady state error, a finite number of a steady state error, or your steady state error does not converge. So that's the principle that I want you to remember. So here's the type of system that we're talking about. So here is our open loop transfer function for this system that has an input, it has a transfer function, and then an output. It has feedback over here. So this transfer function is the open loop transfer function. And analytically, for a system like that, the steady state error is computed this way. So it is the steady state error in the time domain is the limit of the error expression. Actually, this here, I'm sorry, that is a typo. It should be as t goes to infinity, okay? Remember that the mapping of the time axis to the s-plane is that if t goes to infinity, s goes to 0, okay? So that is a typo, I'm sorry. So we can take the limit of the time expression of the error, which is the difference between what we want and what we're really getting. And if we do that in the transform domain, that becomes the limit as s goes to 0 of the error expression, which in terms of the input and the open loop response is this expression over here. So if we assume that the transfer function is either is a power type expression. So we have the unit step, which is sort of a constant. Then we have the ramp, and we have the parabola, those three. So we can see that the Laplace transform for the or for a scaled unit step is just a constant. So essentially, the Laplace transform for exponential type signals is the constant associated with the signal divided by s raised to the power of the signal. So for a ramp, the Laplace transform would be a divided by s. For a parabolic input, the Laplace transform would be a divided by s squared. Okay? And once we put that input into this expression over here, and if we recall that the open loop response can be decomposed as a rational polynomial of some constant k, and then that rational polynomial expression where I have a numerator on s and a number of poles at 0, denoted by s to the n times a denominator polynomial in s. If I put that in, that expression over here, I get that the steady state error is the limit as s goes to 0 of this expression. And I remember that s to the 0 is 1. So if you do that for the different cases, and the different inputs, then you'll find out something that I didn't put here, that you have for a step function, you would get like Kp, but that Kp, Kv, Ka, which stands for position, velocity, and acceleration, is really tied to the old days when they were trying to do analog control of mechanical systems, so I decided not to put that in there. But you get these expressions for these three inputs and very specific type of mechanical. So it's more of a historical. So I didn't put those equations in there, but the procedure is in there in the previous slide. Okay? And just like we had diagrams, or we can have very complex diagrams that we're going to be using for complex systems, for cyber-physical systems and software engineering systems. The roots of those systems start with this very old historical type of transfer function driven block diagrams that you are familiar with. And they come from the transform and the transfer functions, and that's how the first few complex systems were these transfer functions put together. They were cascaded, they were added, and they also represented feedback systems. So in this case, this is the additive combination of two systems. This is a cascaded system in which the transfer function multiplies. Here, the transfer functions add. And then here is the classic feedback system that you're also familiar with. These are the sort of origins of block diagrams. So what we want to do is remember, and what this chapter is being about is basically a reminder and a review of things that you must have seen or could have seen in control, signals and systems, or will have seen if you have not taken those courses. So that's the end of chapter 1. And like I said, tomorrow we'll do a review of the whole chapter and have some nice Q&A and conversation about what we covered so far. Okay? All right, thank you so much.